In this example, we are going to prove that the summation of this expression from k equal to 1 to n will give us the expression n divided by n plus 1. Let's take a closer look of this expression before we prove this formula. This expression means we're going to add up all the terms here with k start with a value of 1 and n at n. So when k equal to 1, we'll have this expression. Then we add with another value of k, which is 2. Okay, when k is 2, we'll have this expression. We'll continue to add until we reach the value of k equal to n. So the last term, we just substitute the k by n, and we'll get this expression. Now this expression here is the first term. This one will be our second term, and this will be the n term. To start the proof, we will let Pn to be this expression here. So the step 1 of the mathematical induction is to prove that P1 is true. P1 means n we substitute the value of 1. Okay, so the left hand side of the expression, okay, which is this expression, we substitute the n by 1. This will give us, and we know that the summation of k equal to 1 to 1 will be this expression here. So it give us 1 over 1 will be half. Now we are going to prove the right hand side of the expression. When n is 1, we substitute the n here by 1, we will get 1 over 1 plus 1, which is also half. So this will be equal to the left hand side. Therefore, we conclude that P1 is true, since the left hand side equal to the right hand side. For step 2, we assume Pn is true, so we just copy down this expression. For step 3, which is the induction step, we are supposed to prove that Pn plus 1 is true. So what is the expression for Pn plus 1? Okay, we are going to write down. Now, because our last term is n plus 1, we have to write this as n plus 1. And now the n here we are going to replace by n plus 1. We'll get n plus 1 divided by n plus 1 plus 1 will give you n plus 2. This is the Pn plus 1 expression that we are supposed to prove. I would like to start to prove from the left hand side of the expression because it is more complicated. From here we are going to simplify until we should get the expression of this one. Okay, so I start with the left hand side of the expression to do the proving. Now the summation of k equal to 1 to n plus 1 I can rewrite as the summation of this expression, same expression with k equal to 1 to n plus the n plus 1 term. For the n plus 1 term, that means the k here I'm going to substitute by n plus 1. This will give me 1 divided by n plus 1. n plus 1 plus 1 will be n plus 2. Now let's focus on this expression here. In this expression here, if I were to do the expansion, it will be all these terms add together. So this will give us k equal to 1, k equal to 2, and this one will be k equal to n. Okay, but our last term should be n plus 1. So after k equal to n, we should have one term, the last term as k equal to n plus 1. That means we are going to substitute k by n plus 1 here, n plus 1. So I will get n plus 1, n plus 1 plus the 1 here. What can we say about this expression here? This expression is actually the summation of k equal to 1 to k equal to n. Plus this expression here. So let me copy down this expression. Okay, so therefore the summation of k equal to 1 to n plus 1, okay, of this expression can be simplified into the summation of k equal to 1 to n only, the same expression, plus this expression here. Now let me continue to prove this expression. We are supposed to prove the left hand side of this expression. It will give us this expression here. So let us continue on this. So okay, let me copy down this. Now what can we say about this expression here? From step 2, we know that this expression here can be simplified into n divided by n plus 1. So I'm going to simplify this expression as n divided by n plus 1. Now the summation now is gone. So now we are supposed to add up this term, and hopefully it should give us this expression here. The common denominator will be n plus 1, n plus 2. So here I need to multiply by n plus 2. This will give us n squared plus 2n plus 1, n plus 1, n plus 2. If I were to factorize this expression here, it will give us this. And the n plus 1 here, n plus 1 here can be cancelled. So, and this is actually equal to the right hand side of the expression. Now let us conclude step 3. For step 3, if Pn is true, it will imply that Pn plus 1 is true. This is what we have proven for step 3. And overall, since P1 is true, we know that by mathematical induction, MI, Pn is true for all positive integer of n. Okay, what this statement means is, since P1 is true, we have proven P1 is true in step 1. Okay, and in step 3, we know that if Pn is true, Pn plus 1 is true. So now, if n take the value of 1, it implies that P2 is true. Okay, so we have proven this in step 1, and in step 3, right, we know that if P1 is true, P2 will be true. Okay, and P2 is, since we know that P2 is true, it also implies that P3 is true based on this statement again. Okay, and we continue to do, eventually we'll know that Pn is true. Okay, this is the concept of MI.